Hey friends, thanks for tuning in to Virtual Earth Tech. I'm Brett Whitman, the Geology Manager at Grayson Mill Energy. Today I'm going to be telling you about a collaboration study that we did with Premier Oilfield Group, Green Imaging Technology, and H2 Labs. Basically, we did an integration study with XRF and NMR performed on cuttings, and this was a petrophysical analysis that we did to help upscale a high-tier data set from a science well to a lot of vintage cuttings data sets to help us make more robust petrophysical maps in the Powder River Basin. So Grayson Mill Energy just finished drilling their first well this past February in the Powder River Basin, and it's drilled in the northern part of Converse County in the southeastern part of the basin. We took a pilot hole on this well and down to the muddy, and we took a 660-foot core. Afterwards, we kicked off and drilled a 2-mile horizontal in the second Turner formation. We got a great core, 2 back-to-back 330-foot full sections, and additionally, we took cuttings at 5-foot intervals. So this is a great starting point for us to do a cuttings to core workflow. It's also an exciting time to be in the Powder River Basin. There's been a lot of recent development, and operators are focusing on moving their efforts from the delineation phase to the development phase. And many groups are experimenting with different patterns, targeting the first and second Turner benches that are co-developed with efforts in the Niobrara. So we're at the early asset development phase. We have 25,000 acres. We've drilled one well that we're planning on completing later this year. And so we have a very small amount of high-tier data sets. We have our one core and logs, as well as a few other data trades we've executed. And our other data sets that we have to work with are mostly vintage logs and drill cuttings. And these vintage logs are really great for making scoping net pay maps and oil in place maps, but there can be lacking in terms of making more robust maps that show the movable fluids portions. So one thing we came up with was to use drill cuttings. Drill cuttings solve that problem because they're abundant and scalable, and there's a high amount of access to them. So by performing XRF on the cuttings and NMR on the cuttings, we're able to use those to have a more robust view of the movable fluids. So a lot of you might be thinking, okay, another cutting study. Well, there's going to be problems with that. There are several problems and challenges to overcome when doing a cutting study. One is the depth uncertainty. And we have a way that we're addressing the depth uncertainty that Premier's come up with by doing a pseudo gamma ray from XRF. So they take the potassium, the thorium, and the uranium and create a pseudo gamma ray for each point that they're performing XRF. And those are the red dots that you see next to this gamma ray curve. And so then based on the pseudo gamma ray, they shift the XRF to wireline depth. Another challenge with performing NMR on cuttings is the surface fluids issue. So because of the irregular surface of cuttings, you can accumulate fluids on the surface of the cutting. Now, the NMR measurement actually just measures the fluids. So not sure how familiar everyone is with NMR. I'm sure there are petrophysicists listening to this talk, and there's also geologists that are maybe less familiar. But the way that NMR works is it's basically an electromagnet that excites the protons in the hydrogen atoms of the fluid. And it measures how those protons relax after exciting them. And that's the echo train that we see here in this T2 distribution. However, it doesn't actually see the pores, it just sees the fluids. And so if there are excess fluids coating the outside of the pores, it's going to interpret that as porosity. And so that's the overestimate that we see here in green. And we don't want to have that. We want to get rid of that. Some folks in the past have just used an arbitrary T2 time cutoff to try to separate that error, but that seems pretty subjective. So the folks over at Green Imaging have come up with a better solution for this. And so what they do is they put the cuttings into a vial and they centrifuge it. So they spin it around at a certain RPM that removes the surface fluids, but it leaves the fluids inside of the pores. Because the capillary forces that are required to pull the fluids out of the pores is much greater. Afterwards, they rinse it with deuterium, and then they run the NMR on the cuttings. This plot over here on the left is showing us how that works. So we have two different rock types that are showing detected volume lost and centrifuge speed. So you see that the surface water comes off really easy at low centrifuge speeds because the surface tension is a lot less strong of bonds than the capillary forces. Then once you increase the centrifuge speed, you see that some starts to still come off and the pore volume will eventually come out. You'll also notice that the sandstone and the shale have different slopes, and that's because the shale has stronger capillary forces than the sandstones. In addition, Green Imaging does another check, which is basically comparing pseudo cuttings to core plug NMR. And so this is a comparison of saying, okay, we know what the porosity is from NMR from plugs, and we're comfortable with that analysis. Let's crush up this plug and create pseudo cuttings in the same way we would use regular cuttings and see how those porosities match up. So this is something that Green Imaging is continuing to do, and they're adding to this data set. Okay, so we've discussed some of the challenges and how we're going to address those. Now let's discuss the Green Imaging porosity workflow. So we've got both an equation to appeal to the petrophysicists that are listening to this, and we've got a nice diagram so we don't completely lose the geologists here. Basically, the porosity is made up of the pore volume of the cuttings, made up of V cuttings, over the denominator of the bulk volume of cuttings. And so the V cuttings are simply the NMR measurement of the cuttings. And the bulk volume, however, is difficult to measure geometrically. Just imagine trying to measure the volume with a ruler or something of a cutting. The regular surface isn't fit for that. So we have to get at the bulk volume a different way. And so we use V total, which is a vial filled with fluid, and that sees all the porosity that could exist within that vial from the NMR. Then we take another measurement of the NMR after cuttings are added. And so the first measurement minus V cuttings plus fluid gives us the volume of the grains that are made up in the cuttings. So now we have the grain volume, and we add that to an NMR measurement of just the cuttings, and that gives us the V bulk. So we indirectly get the V bulk through that process, and that goes in the denominator, of our equation. So now we've covered the challenges and how we're going to address those challenges, as well as the workflow that's going to be used on the cuttings NMR. And so now we're going to discuss a little bit about the chemofaces and what we did with the core. So the chemofaces are generated from the XRF, and the XRF was completed with a handheld device every 2 inches on the core face, as well as the cuttings. And so basically you take the XRF from cuttings and LECO-TOC measurements, and you put that into spot fire hierarchical cluster analysis, and that generates the facies track that we see on the right of this display. And then those colors on that facies track correspond to the facies in the core photographs. At the top of the Niobrara A, we have alternating chalks and suboxic chalks, and those grade into more organic facies of anoxic mudstone and anoxic marl. We see those facies persist into the lower portion of the A and the upper portion of the Niobrara B, and then that shifts quickly into argillaceous chalks and chalks in the Niobrara B. These chemofaces highlight that this is an objective way of doing core description that captures subtleties that are difficult to measure with the visual eye. For example, the anoxic marl and the chalk, which have very different elemental and pore size distributions, are visibly pretty similar. Then grading below the Niobrara B, we have the argillaceous mudstone, which is an inorganic lean shale punctuated by ashes that divide it from the Niobrara C. The Niobrara C is chaotic and interbedded with marls, anoxic marls, and chalks. The first turner is a completely different animal altogether. So in the Niobrara, we saw organic carbonates and shales. And in the first turner and second turner, we're going to see sandstones and shaly sandstones. And so in the first turner, we have everything from a clean sandstone to a silty sandstone that has varying degrees of bioturbation. And then we have the mixed mudstone, argillaceous mudstone, and sandy mudstone facies that have clay laminations and some bioturbation at the expense of those laminations. In the second turner, the upper portion has a higher percentage of argillaceous mudstone and sandy mudstone when compared to the first. And then the lower portion of the second turner has an increasing amount of clean sandstone that is interbedded with the sandy mudstone, which makes for another good target. Another way we can look at this chemofaces data is we can bring it back to wireline depth and compare it with NMR log total porosity. So this is showing a box and whisker plot of the total log porosity distribution for each chemofaces. And it's also a good reminder that just looking at total porosity from NMR and these chemofaces isn't necessarily going to get us to a robust answer on which facies have the highest reservoir quality, because we're going to need to look at the pore size distributions to understand which of the facies have the most movable fluids. This is our first display showing our results from the NMR cuttings technique. And so the petrophysical tracks on the left show us gamma ray and the pseudo XRF gamma ray. And the second track shows us NMR porosity, density porosity, and the core NMR plugs in black, and the cuttings NMR plugs in green. We see that in the Niobrara B and the first turner, we have a pretty good agreement in comparing the total porosity from NMR cuttings to the total porosity on the log. However, in the Niobrara A and the Niobrara C and this second turner, we didn't have a great match. And so this is a shortcoming of this study, and we are looking for better ways to tighten up that relationship. It seems to also affect some of the more tight facies have more error than some of the more permeable facies. So in conclusion, we're going to look at the pore size distributions to see if we can learn something from them, even though the total porosity does not have the best match. So what we're looking at here are T2 echo trains for both the NMR log and the cuttings NMR. And so basically the T2 is the distribution is related to the distribution of pore size in the rock. And so the way to think about this is that there is a T2 for every depth step on a log, and then there's a T2 for every cutting that we measure. But rather than look at this in terms of depths, what we're doing is we're looking at this grouped by chemofaces. And so what you see is there's a bimodal distribution in this relaxation time, and that's telling us something about the pore sizes. So the first set of peaks with the fastest relaxation time, that is the irreducible volume, and this part in the middle is the capillary bound volume. This second peak is showing us the free fluids. And in unconventional petrophysics, typically people use 4 milliseconds as a bulk volume irreducible cutoff. And it's kind of in flux, but folks use anywhere from 8 or 10 milliseconds for unconventionals. And so when we look at the curves for each chemofaces to this right of the line, that's how we really understand which facies have the most movable fluids. And so for the Niobrara, that's the chalk and the suboxic chalk. When we look over at the cuttings NMR, we'll notice a few things that are different about the T2 distribution when compared to the wireline, but some things that are similar. For example, in terms of looking at the free fluids, the same facies have the highest volume of free fluids, the chalk and the suboxic chalk. But we do notice that in total, the overall relaxation times are shorter. And we think this has to do with the fact that the saturations have changed a lot in these cuttings. The NMR log is measuring in the native borehole native saturations downhole, whereas the cuttings have been flushed with oil-based mud, have been dried, washed, and resaturated. Because the NMR only sees the fluids and the saturating fluid is different, it's very likely and almost expected that we would have different relaxation time profile. But the shape of the T2 distribution is showing that the same facies in both methodologies are showing the highest amount of free fluids, which is significant. So let's look at the Turner. Similarly, we're seeing a bimodal distribution in the NMR T2. We also see that the clean sandstone, followed by the silty sandstone, and lastly, the sandy mudstone, has the highest free fluid pore volume. In addition, when we look at the cuttings NMR, the facies in the same order have the highest free pore volume. So in conclusion, the chemofaces with the largest free fluid volumes were consistent. So both methods that were independent of each other were able to identify the same chemofaces that have the largest free fluid volumes, which is a proxy for the facies with the highest reservoir quality. In addition, the T2 distributions having these similar profile shows as proof of concept. So now we know that we can use these cuttings with XRF and NMR to identify qualitative and quantitatively the reservoir quality across the field scale. Additionally, we recognize we need to do more work to reduce the error between cuttings and NMR total porosity methodology. It also seems that the formations and facies that are less permeable, such as the anoxic marl, need the most work. It may be related to those formations being harder to resaturate in the cuttings NMR workflow. This time, I'd like to thank everybody that helped with this analysis. It was truly a group effort. All the guys at Premier Oilfield Group, including Matt Hemingway, all the guys at Green Imaging, and Mike Dick, and all the guys at H2 Laboratories. At this time, we'd like to take any questions that you have. Thank you.